All right. So here we are. So we're here to cook. We're going to cook up some numbers. There's a famous quotation from Carl Sagan, who some of you may have heard of. He said, "If you wish to make an apple pie from scratch, you must first invent the universe." I don't think he was talking about the same kind of things that we're going to be talking about, but it was a little bit along the same lines. He's essentially saying you gotta, if you want to make things properly from scratch, from nothing, you gotta start with the very fundamental building blocks. And with numbers, that's not something that we often do. We usually just sort of take numbers as they are and just sort of behave as though they have these properties. And in the 19th century, there was a bit of a crisis in mathematics where mathematicians were worried about whether or not we're being rigorous enough. Because maybe we're assuming some things about numbers that might lead to contradictions, and we're just not aware of it because we've never looked at it before. So the question is, how do we know that numbers, which the word number obviously can mean a number of different numbers. Okay. The word number has various meanings, but the things that we talk about as numbers, we want to know what their properties are. And the way that we make them have the properties we think they should have is by building them so that they have those properties. And you'll see in a moment what I mean by that. Okay, so the only thing that I want to just leave as a disclaimer is that in mathematics, there is something called isomorphism. Iso means same, morphism means shape. You can build different structures in different ways and end up with the same properties, and it ends up essentially being the same structure with different labels. So up to isomorphism, I'm building various different things, or we will be building various different things. But you should consider that there are alternative constructions for some of these things. So this is not the only way. Okay, so now let's get cooking. So we're going to start with the natural numbers. So we usually denote the set of natural numbers like this, n for natural. So that's 0, 1, 2, etc. Okay, but what do we mean when we say 0 or 1 for 2? Okay, so to be very, very strict, when we say 0, we actually define 0 to be just a name for the empty set. Okay, so the set containing nothing. When we talk about 1, by definition, that is the set of 0, i.e. the set containing the set that contains nothing. Okay, when we do 2, that is by definition the set containing 0 and 1. Okay, so there's a pattern here. So in general, you should think of it. So this is not like good notation, but you should think of it as n being defined as the set of 0 through n minus 1. Okay, that is generally how you should sort of think about it. And the reason we define it this way is because that allows us to define things like less than, things like addition and subtraction, which we will get to now. Okay, so here's what we're going to do. We're going to try to make these make the structure have the properties that we expect of the natural numbers. And the way we're going to do that is we're going to define n is less than m for two natural numbers n and n, if and only if n is actually contained in m. Okay, so I put less than or equal to and contained or equal to, but obviously if they're the same, then they're the same. If they're not the same, then they're not the same. Okay, so we have this definition. So what does that mean? Well, it means 1 is less than 2 because 1 is actually like inside 2. Okay, so the other way of writing this is this. those actually end up meaning the same. So if n is an element of n, so 1 is actually an element of 2. Okay, 2 is a set that contains the number 1 in it. And in general, n will contain all of the numbers up to n minus 1. And another way of thinking of it is that 1 is a subset of 2, because 1 is the set of 0, and 0 is in 2, so 1 is a subset of 2. So either of those will work for the natural numbers. We just choose one of them. And then once we have chosen that one, we're going to run with it. Okay, so how are we going to think about so the next number? We have this idea of consecutive numbers, right? I didn't just start from anywhere. I started from 0 and then 1, 2, and so on. And we have this idea of n minus 1. So we got to put in addition or something somewhere in there. So so here's the idea. We have this thing called the successor function. And the idea of the successor function is that for each natural number, we can find a successor, just a number that comes right after it. Okay, so I'm going to denote that successor function with s. So it's pretty straightforward that s of 0 is 1, right? And in general, you should think of s of n as equaling n plus 1. What you think of as n plus 1 is s of n, but we haven't defined plus. So this is just what you're thinking right now. It's not, doesn't mean anything yet. Okay, and the definition of the successor function is that s of n for some natural number n is just the union of n with the set containing n. Okay, so n is the set of, right? So in other words, it's this set. Okay, which by definition is n minus 1. Okay, and we can just, so we have these names, 0, 1, 2, and so on. We're using these names to describe these numbers, but at the end of the day, this is what's going on. There's just these like extremely nested sets. Okay, and we can define this successor in such a way that we can just generate the natural numbers by starting with 0 and then adding the successor of each number as we go. Okay, so before we even define addition, before we even move any further than this, we can prove something cool called the principle of mathematical induction. There we go. And what the principle of mathematical induction says is that if A is a set of natural numbers, okay, so this is, A is a set inside of n, and 0 is in the set A, okay, and for any element of A, so for any number that's in A, the successor of that number is in A. So this is notation heavy, but I said it out loud. So then that means A must be the natural numbers. There's no other, we can't make any other subset or whatever that's going to have this property. Okay, so how are we going to prove this? Okay, so to state it again, if A is a set inside the natural numbers, and 0 is in A, and for every number in A, the successor of that number is in A, then A must be the whole natural numbers. Okay, so how are we going to prove this? So we're going to prove this by contradiction, right? So we're going to suppose that's not true. Suppose A is not equal to n. Okay, so because n is well ordered, it's got this nice ordering property, we know that there must be at least n, so then there exists a least n in the natural numbers, such that n is not in A. Okay, so A is some subset of the natural numbers. Since we're assuming that A is not the whole thing, there must be some kind of natural number in there, in n, in the set of natural numbers that's not in A. Okay, so now we're going to choose, so we don't know a priori that n is the successor of something, but we do know by the well-ordering of the natural numbers, we know that there's a greatest n, okay? There exists a greatest, I can't write, greatest m such that m is less than n. Okay, so for any natural number, this is again from well ordering, just because the natural numbers have this nice order to them. If you cut it off at some point, then you have finitely many numbers left. You just have this like initial sequence of natural numbers, and then there's going to be a greatest element to that, right? So we're cutting it off at this n. We're just looking at the first few, so these are things that are supposed to all be in A, and then we have this greatest natural number n. Okay, but then the successor of m must be in A, right? So now we have a problem because the successor of m must be either n or something between m and n. If it's n, then we have a contradiction because we said n was not in A. If it's something between m and n, then we have another contradiction because we said m was the greatest number less than n. So either way, we have a contradiction. So a contradiction, and so that means the assumption that we made here, which is that a and n are different, must be false. I'm using the whole blackboard just in case you guys are not there. Okay, so we proved this. It doesn't seem like a very difficult fact in the sense that it sort of makes sense. You know, we can just make the whole natural numbers by starting with 0 and just taking successors. But it is an important fact because it gives rise to a whole new style of proof, which is proof by induction, which we're not going to use today, but it's important and useful. Okay. Okay, so now how do we define the other operations? I'm not going to go into them with too much detail, but I'll try to satisfy you that we are able to define these things in a way that is consistent. So how do we define addition? So we're going to start with defining a plus 0 to equal a. That's easy enough. This is just by definition, a plus 0 is a for any natural number a. And if we take a number a and we add the successor of some other number b, by definition, we're going to say that this sum is equal to this, the successor of a plus b. Okay, so successor of b is a bigger number than b. So what we do is we've essentially defined this inductively. We've got a plus 0, and using that we can figure out what a plus 1 is because 1 is the successor of 0, and so on and so forth. We can keep defining these sums, and so addition will end up making sense for the whole natural number line. In particular, we can prove a claim. So if I claim that 2 plus 2 equals 4, I can actually prove that from the definition, right? So 2 plus 2 is definitely equal to 2 plus the successor of 1, right? And so that's equal to the successor of 2 plus 1, right? So that's equal to the successor of 2 plus the successor of 0. So it's equal to the successor of 2 plus 0. So it's the successor of 2, so it ends up being 4. So anytime you sort of apply the definition like this, I don't know if this really requires a square, but we've now proven that 2 plus 2 equals 4. Okay. From first principles, we know that this makes sense. Okay. Oh look, more people. Okay, so all of the usual properties that you're used to from addition follow from this basic definition. It's like deceptive because, okay, so for example, we haven't said that a plus b is the same as b plus a, but it turns out that you can derive all these things from here. Okay. So now we'll move on and we'll define our next structure. So here we have the natural numbers. And we've proven something interesting about them. We've made this operation of addition. We can also define multiplication, but it's not it's not necessary. It's the same. It works the same way. So the way actually we may as well just do it. So we can also define A times the successor of B is equal to A plus A times B. So now that we've defined addition, this will make sense. So this is again inductive. So we have to start off from somewhere. So we just say A times 0 is 0. Okay, and then these two things function exactly the same as these two things, and you can prove very similar facts, like that 2 times 2 equals 4, using these two axioms that we've defined for ourselves in the natural numbers. Okay, but more interestingly, let's continue to build more structures. So the natural numbers are these relatively straightforward, I guess, things where we just have these sets that are nested in each other, and we just have each number containing all the numbers before it. Now we want to model some other properties of the integers, right? We want to have negative numbers. We already have our 0, and we have addition, but the idea of subtraction isn't really useful if you can't have negative numbers. So we're not going to bother to define it here. What we are going to do, so the integers are usually denoted with a z like this. What we're going to do is we're going to define integers as pairs of natural numbers, or it's more accurate to say equivalence classes of pairs of natural numbers. So when we have a pair, a1, b1, we call that the same integer as another pair, a2, b2. So this is in the integers. If and only if a1 plus b2 is equal to a2 plus b1, and this is in the natural numbers. Okay, so these a's and b's are natural numbers, and you can think of this guy as essentially a minus b. We haven't said that it's a minus b because we haven't said what minus is, but this is essentially what you're thinking of, because if you just add the two things back in, just a straightforward algebra there, then you end up with the same properties that you'd expect. And what this allows us to do, first of all, it allows us to make a pretty graph. So I'm going to go ahead and do that. So if this is A and this is B, we have this like lattice here that we can draw. And then I get to use some color. So everything along this dotted line is the same thing, and everything along this dotted line and this dotted line. Each of these things are the same integer. Here we have this line comes out to the integer 0, because here we have a is 1, b is 1, a is 2, b is 2, so the a minus b is always going to be 0, so these guys are all going to be equivalent, they're all going to be what we call the integer 0. Here a is bigger than b, we have the integer 1, and then we have the integer 2, and conversely on this side, these lines represent minus 1, minus 2, and of course you can continue this to infinity. So it does actually kind of look cool the way we've defined this, even though we're just defining the integers here. Okay, so again, think of this as a minus b. And based on this we can define for example, addition. So a1 b1 plus a2 b2. So again, so these are the names we would normally give to the integers, right? This is just a lot nicer to write. But when we're defining how to add things, we want to be able to work with it at this level, to look at it as a pair of natural numbers, because of the way we're going to define it. So we're going to define this as a1 plus a2, b1 plus b2, like that. Yeah? Yeah. Okay, so why do we define it this way? Well, what we want to think, so again this is in quotations, but what we want to think is that this is a1 minus b1, and we're adding a2 minus b2, right? And as we group the terms, we end up with a1 plus a2 on the positive end minus b1 plus b2 on the negative end, right? Okay, so now we've defined addition in the integers, and you'll have to trust me that multiplication works similarly. You just sort of expand what it would look like if this was actually a minus b, and then you essentially make it work for you this way. Of course, I'm speaking in sort of broad terms. You can't make anything, just anything works. It has to be consistent, but you can make it work with the same sort of strategy. Okay, so now we've defined the integers. We know that we can do the things that we're used to be able to do. Yes.
Did you define so let's say you defined an arbitrary integer, let's say -1,
yeah,
to be the set of those pairs? So can you give an example of, so like a pair in this case would be like 1, comma 2?
Yeah, so like 0, 1 is -1. This is what we call -1. But we could also like do instead of 0, 1 we could do 1, 2. That would also be -1. Right? Because what you're thinking is this guy minus this guy. If we were to check whether or not these are equal, right? So these are our A's and these are our B's. So we want to see if A1, if A1 plus B2 is equal to A2 plus B1. So 0 plus 2, is that equal to 1 plus 1? It is. Okay? So then these are actually the same integer.
Right, so I don't doubt that those are the same integer, but how do you actually assign -1 to those pairs?
We just call it -1. -1 is just our name for it. Okay, so we can define negation. So the negative of A comma B is just defined as B comma A, like that. Okay, and so we call this -1 because it's the negative of the thing that we call 1 naturally.
Right,
But it's just a name. -1 is just a name.
But if I give you an ordered pair,
Yeah.
you have it in your hands, how can you tell me what integer it corresponds to?
So the way you would do it is you would subtract 1 from each of the coordinates. So suppose you start with 2, 3, like that. You'd subtract 1 and then you'd end up with 1, 2, and then you'd subtract 1 again and you end up with 0, 1, and you see that the 1 is in the second place, and so you would say, okay, this must be -1. Oh, you don't
Right, but you don't have subtraction.
So you can define subtraction as well. I skipped it. But
Okay,
but you can,
sure.
Yeah, you can do it. At the end of the day, it's not so important that given an ordered pair, you're able to find an integer. It's more important that we have this structure and we have names for these things. But you could do it. It would be painful to work with ordered pairs instead of integers as we're used to. But you could do it, and this is a structure that has the properties that you'd want. It's the only construction that I found for the integers that was like nice. I suppose there might be other ways to construct the integers that would be less nice, but this works reasonably well. So yeah. So I'll leave it there. Okay. The integers are actually, so they're cool and stuff, but they're more exciting to me because they allow us to define the rationals. So the rational numbers, we write this as Q because R is taken for the real numbers you'll see later. Okay, so with the rationals, we're talking again about ordered pairs of integers this time, but instead of writing them like this, which is how we normally write ordered pairs, we write them like this. Okay, and we say that A1 over B1 is equal to A2 over B2. This is in the rationals, if A1 times B2 is equal to A2 times B1. So we are doing exactly the same sort of idea as we had in the rationals, in the integers, but we're doing this with respect to multiplication, which I didn't define there, but you'll have to trust me, we can define it in sort of the usual way using this kind of idea. Okay, so we end up with this definition. Okay, so that means that like 1 over 1 is equal to 2 over 2, and so on and so forth. There's actually sort of a common technique. You can do this with things other than the integers. Say, it's what's called a ring of fractions. And all you have to require is that these b's, these denominators, aren't allowed to be 0. Without loss of generality, we can also say that the b's aren't allowed to be 0 or negative numbers, because if you have a negative b, then you can just flip the sign on the a, and you'll end up with the same rational numbers. So, it's convenient to consider only positive denominators, but in principle, you can have negative denominators. It doesn't matter. Okay, so how are we going to define less than? Actually, before we define less than, let's make a graph of this as well. So, here we have a and b, and here we have our lattice points, because again, the integers are discrete. You can't just find them wherever you like. And this time, instead of, so I'll use a different color because this is a different structure. Instead of making the lines parallel this way, so this is supposed to be straight, we're actually going to draw the lines this way. So everything along here, so this is 1, 1, right? 1 over 1 is the same as 2 over 2 is the same as 3 over 3, and so on. This is 1, or 1 over 1 if you like. And here we have a 2 over 1. A is 2, B is 1. So 2 over 1, so everything over here, you're going to have a 4 over 2 over here, and you're going to have a 6 over 3, and so on and so forth. So this is going to be 2. And then similarly, this guy is going to be a half, and then the angles in between will correspond to the various rational numbers. This is only the positive rational numbers. I can go past this way and get negative rational numbers. But you can see sort of the idea and how this is going to look. Again, the graph is not, just as in the integers, the graph is not like super useful. It's just kind of neat. So in some sense, the integers are like parallel lines, and the rationals are like radial lines. Okay, now let's define some things. So we want to be able to say that something is less than something else, right? So we're going to define less than in very much the same way. So a1 over b1 is less than a2 over b2 if and only if a1 times b2 is less than a2 times b1. And this is well defined in the integers, and so this definition will hold nicely. Okay, so we're reusing the same tricks a little bit. We can define addition and subtraction in just the usual way. To add, you just multiply the denominators together and do the gymnastics that you need to do with the numerators. But we're not going to go through that definition. It's a little bit tedious. But instead, I just want to note a property that we had here. So each time we're doing this, we are picking up new properties. So with the natural numbers, we just had this discrete ladder, and it started somewhere, and it just goes up discretely by one step at a time. Each natural number has a next number. There's always a subsequent number, a successor. With the integers, we don't technically have a successor function, but for each number you can go up by one in little steps, and you can go down by one in little steps, and you've got this idea of consecutive still preserved. With the rational numbers, there's no such thing as consecutive. They're dense. So anytime I have two rational numbers, I always know that there's going to exist another rational number such that it's between them, this way or this way, right? If y is bigger than x, then there's going to be some z in between x and y that's going to be there, and the same thing if x is greater. Okay, so this density makes the rationals infinite in sort of a different sense. With the rationals, they go infinitely in either direction, but also between two numbers, you can find infinitely many other numbers, right? You can take you can do like the Zeno's paradox thing, and start here, and I want to get to this line. Well, I can go halfway, and then I can go halfway to the rest, and halfway to that, and so on and so forth. And each one of those is a rational part of the way, and so I've got infinitely many rational numbers in just this finite space. So that's pretty cool. And it's a property that we didn't have before. And you might think, okay, well, at this point all the gaps are like totally filled, we're fine, so we're kind of done, right? Of course we know that we're not done, and Pythagoras refused to accept that we're not done here, but we're not. There's this idea of the real numbers, which I think are probably the most hotly contested definition out of these. There's a little bit of controversy around it, and there's a few different constructions for this. If you look up the real numbers on Wikipedia, you'll see there's like 5 different constructions on there. But here's the most popular one, and the one that I think makes the most sense. Okay, so a real number, which we're just going to call R for real, is a subset of Q. It's a subset of the rational numbers, such that we fulfill these 3 criteria. So A, R is not the empty set, or all of Q. Okay, we don't want it to be either of those things because it just doesn't work out with our system. B, we want it to have this property. So for any two rational numbers, we want to know that if y is an element of R, if y is in this subset that we've chosen, and x is less than y, then x is also in our real number. Okay, so we'll draw for a second what this means, or we'll draw in a second what this means. But essentially, what's going on here is that we're choosing our cutoff point, and then we're including everything to the left of that cutoff point. Okay, so that's what a real number is. Okay, and the last thing is also a little bit of a housekeeping criterion, which is that R has no greatest element. So we're using strictly less than instead of less than or equal to. Okay, and that's going to become useful in a bit, but it's a bit of a housekeeping item. So the idea is we have this line, which I'm drawing it in a straight line, even though of course we know that there's all these holes for the irrationals that are coming up later. And so what we're saying is, for example, 0. Here's 0. 0 contains everything over that way. Okay, so this is supposed to be like a closed bracket. 0 in the rationals, or sorry, in the reals, is defined as the set of rational numbers. So actually, maybe I'll write rationals as a over b, just to emphasize that these are rational numbers, such that a over b is less than 0 over 1. Okay, it's the set of negative rational numbers. We can do exactly the same thing with the number 1. It's the set of everything on this side. And you can already see 1 contains 0, right? 1 is a subset of the rational number that contains everything that's in 0 plus a little bit more. Okay, and then we can also say the square root of 2, right? How do we define the square root of 2? So I'm not going to go through the proof of it, but we all know the square root of 2 is irrational. It's not a rational number. So how can we define the square root of 2? Well, not quite this way. What we're going to do is we're going to define the square root of 2 like this. The set of rational numbers such that a squared over b squared is less than 2. Okay, so when we square that rational number, we get less than 2. Or if that rational number is negative, then we'll take that too, because if you square, for example, if you square minus 4, then you end up with positive 8, and then that's not less than 2, and whatever. We wanted to include everything over this way, so we'll include all the negative numbers. So we have this sequence of rational numbers, and we can get as close as we want to the square root of 2 in the rationals, but we can't actually get there. Everything that's less than the square root of 2 is in this set called the square root of 2, which is a real number. Okay. Questions? This is a little bit counterintuitive. It's called Dedekind cuts. The guy who came up with it was Richard Dedekind, and it's as late as the late 19th century. So, yeah, not super new. Yeah.
Did we define squaring already?
So square is just multiplication by itself. So we didn't define multiplication, but I assured you that multiplication exists. So rather than writing it this way, I could have written just a over b times a over b, and then that would have meant the same thing. Defining other real numbers like, just a second, defining other real numbers like pi or e is more difficult, but it is still possible. It's just more complicated, and we're not going to get into the details. Yeah. Okay. Yeah.
Did you say that Q was a subset of R? There.
So no. So it's a subset in the sense that we can find for each rational number, we can find the set of real numbers less than it. So we have like a buddy system. Okay. We have a structure in a set of points in the real numbers that behave like the rational numbers, and for all intents and purposes, they are the rational numbers up to isomorphism. But like strictly speaking, based on this definition, Q isn't a subset of the rational numbers because the real numbers, because no real number is all of Q, and however high you go up, there's always going to be like a boundary. Yeah.
In your definition, is there a reason for the strict inequality, or could it be less than or equal as well?
Okay, so here's
but then it would be in its own set.
You could do it that way.
You would have rational numbers that would be in their own set.
So it would sort of work because you could do it, and then in this set, if you make this less than or equal to 2, then this would be, irrational would mean that it doesn't contain a greatest element. But this way just sort of keeps it uniform. The only intention, I think, of this axiom is that is that you don't have like two different sets, that one of them has this greatest element and the other one doesn't, and otherwise they're the same. So just so that there's no confusion between the two real numbers, essentially. Okay. But that is a good point. It is a little bit.
Could you do this with any dense set that has well ordering?
The rationals is not well ordered, but yes, you can do it with any linearly ordered dense set. So, like in principle, you could do Dedekind cuts on whatever you want, but this is the most famous application, the first one. Yeah.
I'm just gonna say I don't think it really matters if it's a strict less than, because the nature of the Dedekind cut is kind of like a limit, but it don't have a concept of a limit yet, so the limit of the equality doesn't exist yet. So it doesn't really affect the
Yeah. You just have to choose one though. That's the most.
Well, like you'll never choose the other one because we don't have a concept of a limit yet. Like where you have to close.
I mean, you could put this as a less than, and you can put this as a less than or equal to, and they would work the same way, because you wouldn't be able to, as long as you're consistent in the way you do it. Like it wouldn't matter for a set like this because it can't contain the square root of 2. Yeah. As I said, I think the more important quality, or this is a very important quality. This is the sort of key quality that I think is that was the heart of the idea, and the other two I think Dedekind came up with to try to make that work, try to make that make sense. Anyway, so we haven't defined things like less than. But I have hinted at it. So we have a 0 that's less than 1. We want 0 to be less than 1. That's something we'd like to happen. We also can see that 0 is contained in 1. Because 0 is all the rationals on this side, and 1 is all those rationals plus a few more. So the way we're going to define this is that R1 is less than R2 for two real numbers, if and only if R1 is contained in R2. Contained, but not equal to, right? We're just defining less than. Of course, if it's equal to, then it's equal to. Okay, so that's one way we can do it, and we can also define addition from here and multiplication. It becomes a little bit complicated because you're working with these sets and you have to take like complements and stuff. But so we're going to leave it. But I just want to leave this guy up there with like a little heart, because I think that's beautiful. We started with we started with the positive integers, with the natural numbers, and we had this going on, that a number is less than another number if it's contained in that other number, and then here we're back to it with the real numbers. And it's both an elegant definition and something that's come up twice now, so I think it's beautiful. You're of course welcome to disagree. Okay, we're also, so as I said, we're picking up qualities, right? We're picking up properties. And so one important one is completeness. So the real numbers are not exactly unique, but very very special in that they have this property of completeness that the rationals don't have. What completeness says is that for every set of rational numbers, so for every so not of rational, sorry, for every set of real numbers, numbers that has an upper bound, there is a least upper bound. And this is a really important property. The real numbers are what's called an ordered field, which means that there's an ordering, and you can do addition and multiplication, and everything has inverses, and it's really nice. Everything except 0 has multiplicative inverses. But this property of completeness is very unusual among ordered fields. We can make a whole bunch of different ordered fields, but only one of them will have completeness, and that's the real numbers. And in some of the research in model theory that looks at ordered structures and ordered fields in particular, this is like an easy way of telling that something is not the real numbers, is by checking whether or not it has completeness. Because you can construct arbitrary structures and you don't know if they're the same up to isomorphism as the real numbers. Okay. Yeah, so there's all sorts of definitions of addition and multiplication that we won't get to. I want to just say a word about the complex numbers. So most of us in this room are familiar with the complex numbers. They're of the form x plus iy for x and y real numbers. And the way you would go about defining this is by saying x plus iy is defined as this ordered pair, x, y. And then from here you can define all of the normal arithmetic facts just with this ordered pair. So when somebody tells you, yeah, don't worry about complex analysis, it's literally just R2, they literally mean it is literally just pairs of real numbers, except that we've defined addition and multiplication on them in a way that we don't usually do with vectors, or that we hadn't done before with vectors. Okay, so now we're finished in a sense. There's obviously an infinite number of other structures that we could construct, but we're not going to do that because I think we've cooked ourselves a large enough feast. And rather than cooking up some more, we should perhaps get to actually tasting this feast that we have cooked for ourselves. So we'll discuss cardinality for a moment. So we'll say this. So A and B are sets. This is going to be a recurrent theme, so just remember A and B are sets of things. Okay, so A and B are sets, and if there exists some kind of function that goes from A to B, such that whenever you have f of A1 equaling f of A2, that's only if A1 is actually A2. That is, it's 1-to-1. Okay? If you have something like this between those two structures, then we say that A is smaller than or the same size as B, like this. So this notation means the size of or the cardinality of. And in particular, if you can do this forwards and also backwards, so essentially you have a buddy system, you can find for each person or each member of A, you can find a unique friend in B, and for each friend in B, you can find its friend again in A. Then we say that A and B are equinumerous. And then we write that as the cardinality of A is equal to the cardinality of B, like that. Okay, so that's nice and straightforward. And I can convince you that, for example, the cardinality of 3 is less than or equal to the cardinality of 4, because if we take the actual number 3, which looks like that, and the actual number 4, which looks like that, I can find a really nice one-to-one function that will take this 0 to that 0, and that 1 to that 1, and this 2 to that 2. Oh, sorry, that should be 3. Okay, and so 3 must be smaller than or the same size as 4, but we can't do the other way, because we're always going to have, we can cook up whatever we want. We can do 3 to 0, 2 to 2, and 1 to 1. But then we've got this like 0 hanging around. We're not going to be able to do it the other way. Okay, so in this case, 3 is strictly smaller than 4. Okay, so why is this useful? Well, of course, it's not very interesting when you're looking at like a pair of natural numbers and trying to tell which one is bigger than the other. Instead, we can look at bigger sets. In particular, it is interesting to look at infinite sets. Okay. So we're just gonna say before we look at our first infinite set, it is possible. We don't know. We're wading into this naively. Okay? We're gonna pretend we don't know anything yet. We're gonna say there might be different kinds of infinity. Maybe not. But there might be different kinds of infinity. And so we want to have a special name for things that have this size, the same size as natural numbers, and so we're going to call that countable. Okay, so maybe all infinities are countable, maybe some of them are uncountable, who knows? Okay, I mean some of us know, but we'll get there. Okay, so I'm going to make a claim. We're going to taste the natural numbers, as it were. So I'm going to say n is self-similar. Oh, that should have been this. And in particular, I'm going to say, so what does it mean by self-similar? It means there's a strict subset of n. There's a set that is inside n completely. Every element in that set is in n, and yet it's the same size as n. Okay, how is this possible? If it's missing elements from n, how can it be the same size as n? Well, I'm going to find a set like that, and it's actually a set that's pretty familiar. So this guy, the set of square numbers. So for every natural number n, this guy has the square of that number. And because we have multiplication defined, this is just that number times itself. So this is straightforward and it works. Okay. So this is a set that's not only contained in n, it's like the minority of n. Like if you go to like arbitrarily large numbers and you just choose one at random, almost certainly it's not a square number. So this is pretty rare property as you get high up. Okay. And yet what I'm claiming is that this set is just as big as n itself. How am I going to do it? Well, let's build our bijection, right? Let's build our buddy system. So each time I'm taking in a natural number n, and I'm going to spit out a square number s, right? So 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, and so on and so forth. We can agree on this? It's good? Like secretly I'm thinking, like, oh my god, did I mess something up? This can't be really easy. Okay, so you can see that there is this mapping. We have this buddy system that we can choose. And we can actually go backwards from the set of square numbers. Every square number will have a friend in the natural numbers. And every natural number will have a friend in the square numbers. So actually this is totally valid. This is bijection. Even though this one seems to be going up way faster, this actually works out. We're gonna hit all of them by the end, as it were. So this function works, and I'm just gonna leave it like that because the rest of it I said out loud. Writing takes time. Okay, so we have this infinite set that's self-similar, and actually all infinite sets are self-similar. But this one is, cool proof. All right, so let's make another claim. So we're gonna pick up our structures as we build them. So I'm gonna say that n is equinumerous with z. So there's just as many natural numbers as there are integers. If you think about this for a second, it might seem strange because the natural numbers, goes infinitely in one direction. You start here, and then you take little steps, but you take those steps in just one direction, just to the right. With the integers, you take those steps to the right, but you can also take those steps to the left, and you can go however far you want in either direction. But still, there's a really nice bijection between them, a really nice buddy system, and so I'm going to denote it the same way. Okay, so here's our natural numbers, so 0, 1, 2, 3, and so on. And for our integers, we'll again start with 0, 1, and then we'll do -1, and then we'll do +2, and then 4 will correspond to -2. And you can sort of see the pattern here. I don't need to give too much detail. You can see that this is going to work, and we're going to eventually cover everything. For every integer, there will be a natural number corresponding to it, and vice versa. Okay. So we've proven that. Okay, so now we're on a roll. Okay, we've proven 2 things in the space of like 3 minutes. So we can continue this roll, continue with our mathematical momentum. While the stovetop is still hot, we can put another pot on it. And so I'm going to make another claim. Specifically that the natural numbers are equinumerous with the rationals. Okay, so we've built these structures, and the integers we can see how 2 times infinity is still infinity. So it's not strict. Nobody I didn't say that. But somehow if we multiply the natural numbers by 2 in a sense, we're still fine. We still have the same number. But here, Q has a different property. Q is dense. Right? So it has all the natural numbers in it, and it also has infinitely many things between any 2 natural numbers. So the claim that these 2 are the same size requires some proof. Okay, how do we prove this? So again, I'm going to operate under the assumption that our denominator is positive. It doesn't really matter. It's just a little bit simpler. And then up here, we're just going to list integers, right? So we already know the integers are the same size as the natural numbers. So as long as we show that they're the same size as Q, then we're fine. Okay, so here I'm listing, positive. Here I'm listing the integers, and then here I'm gonna sort of go down, and we're just gonna look at the positive denominator. So this is 0 over 1, this is 0 over 2, 0 over 3. And here we have -1 over 1, -1 over 2, -1 over 3. -2 over 1, -2 over 2, -2 over 3. So we do have some repeats. I don't claim that this is a particularly efficient system, but the important thing about this system that we want to know is that every single rational number will be listed here at least once, right? Everything will appear at least once, and in fact, they will all appear infinitely many times. Okay, so what do we do with this? Well, we need to. This is like a table, right? We need to turn this into a list. All we need to do in order to turn this into a list is start here and then just go around this way. Now again, I don't claim that this is the most efficient way of doing it. Certainly, we're going to come across a lot of repeats, but what we can do when we're making this list is just include the rational numbers that we haven't included yet. Okay, so every time we come across a repeat, we just don't notice it and move on to the next one. And so you have this list, 0, 1, a half, -1/2, -1, and so on. And this list will include every single rational number on it. Okay? And vice versa for every single rational number, it appears somewhere on this list, so we can find the natural number that corresponds to it. Okay, so what that means is that even though they're dense, the rationals are still countable. Okay. Questions? Does this make sense? Slightly mind-blowing, maybe? Okay. Okay, so now you might be starting to suspect that I've been leading you astray. And that when I suggested that perhaps there are different kinds of infinities, I was actually pulling your leg, because we can just do this for whatever we want. Okay, so now I'm going to say that I wasn't pulling your leg, and that actually the natural numbers are strictly smaller than the real numbers. There's like less, there's literally fewer natural numbers than real numbers. It's a different kind of infinities. The other way to say it is that the real numbers are uncountable. Okay, so how do we prove this? So this proof was originally due to Cantor, a guy by the name of George Cantor, and this proof also comes from the same guy. So it's enough to prove that there are uncountably many things in just the interval between 0 and 1, right? So we're just going to look at that interval, and if there's uncountably many things in that interval, then there's no chance that the whole real numbers will work for us. Okay, so suppose we do have a list, and I'm going to write it this way, just for convenience this time. So 0, 1, 2, 3, 4, here are our natural numbers, and here are our real numbers on the other end. So between 0 and 1, right, so we have, for example, 0.1396, and so on and so forth, and it might be repeating or might not be repeating. And then this one is 0.87432, and again, it could repeat or not, and then here we have 9, 5, 6, 11, and so on, 0.22321. And I'm reading these off of my notes because it's quicker than coming up with them on the spot, but you'll believe me, I hope, that it doesn't really matter which I chose here. Okay, and now what we do, okay, so suppose we have this list, we're assuming that we do have this list, and then so we can just make a new number by choosing these guys, right? So we just go along the diagonal. And so we do 0.17629 and so on. So here we have 0.17629 and so on. And we'll always be able to continue this number for however many digits we want because we'll have more numbers later in our list. So this number is fine. What happens if we change each and every digit in this number? So for example, I could choose 0.28730. Okay, that is another number, and it's going to continue. We're just, all I've done is systematically just changed every single digit. And so we have this new number, and we're guaranteed that this number is not on the list. Why are we guaranteed that this number is not on the list? Because it's different from the first number, because it has a different first digit. It's different from the second number, because it has a different second digit. It's different from the third number, because it has a different third digit, and so on and so forth. Because it's different at each digit from one of the numbers, and it's different from every number on this list at some point, it's got to be not on this list. It can't possibly be on the list by the way that we've built it. Okay, so now we have a contradiction. We assumed that we could make a list that would contain all of the numbers, all of the real numbers between 0 and 1, and then we tried to do it. We assumed that such a list might work, and then we proved that it doesn't work. We proved that we're missing something. So that means it's impossible, and that means that that interval, and thus the whole real numbers, is uncountable. Okay. Make sense? Okay. So this is a little bit mind-blowing to see for the first time. I think it's also still cool to see for the second and third and 10th time. Okay, but now this is something that I think most math students will have been familiar with at some point. Now we'll move on to something a little bit different. So we have this thing called a power set. So for a set A, the power set of A, so again, A is just a set, any set. It's the set of subsets of A. Okay, so for example, the power set of the natural numbers will contain, the power set of the natural numbers will contain the set of 0, 3, and 5. It will contain the set of square numbers. It will contain the set of even numbers, and so on and so forth. Those are all sets that will be elements of this power set. Okay, and you may recall from the way we define the real numbers that the real numbers are part of, they're not all of it, but they're part of the power set of the rational numbers. Because each real number is a subset of the rational numbers. Okay, so here's an interesting theorem. This is called Cantor's theorem, because like many other results in cardinality, George Cantor came up with it. Okay, and Cantor's theorem claims that for any set A, set A, the power set of A is strictly bigger than A itself. Anytime you take a power set, you get something that's strictly bigger. If you take the power set of two things, then this will clearly work because you can choose, so you have this set 0, 1. Well, you can choose a number of different subsets of that. So you can choose this itself, that's a subset. You can choose the empty set, you can choose the set containing 0, and you can choose the set containing 1. And so you have, the power set is of size 4 and not of size 2, so it's strictly bigger. Okay, but how do we prove this in general? And specifically, how do we prove this for infinite sets? Because for infinite sets, we can't just verify this for every single case. Okay, especially if we don't know that it's a countable set, then we have a real problem. Okay, so here's how we're going to prove this. So suppose we're going to suppose for a contradiction that we can do this, right? Suppose that we are able to do this. We have this function which goes from A to which goes from A to the power set of A. And this function works both ways. We can go back and forth. Let's say as required. Suppose there exists this function. Okay, so then we're going to carefully define this this subset. So B is the set of A and A. So the set of elements of A, such that when I take f of A isn't in it. So when I take the f of this A, I'm going to end up with some subset of our original set, right? And then I want this to be the collection of all of these instances where I map it to something that doesn't contain it. I map it to a subset that's totally off somewhere else, right? So if we're thinking of the real numbers, if I, for example, had a number here and then it mapped to this subset, then that would be in here, okay? And that's called a non-selfish element. Okay, so this is the set of all non-selfish elements, this set has a really peculiar property because if we assume that this guy works for us, every guy or every girl or every element in the power set of A has a friend, has a buddy in A, then this guy has a buddy, right? So B must equal f of x for some x. Right? Okay, but then we have a problem. Because is x a member of B? If x is a member of B, right? If x is a member of B, then that means x is a member of f of x, so then x can't be in B. But if x isn't in B, then x isn't a member of f of x, and so x must be in B. So we have this contradiction. We can't have it both ways. And so for that reason, just as we proved that we can't have a list of all the real numbers, we've also proven that we can't have this function between a set and a power set that satisfies what we want for a bijection. Okay. So we've proven that as well now. Okay. So questions? Does this make sense? Okay. Okay. Okay, so this is, so now we're gonna move on to the dessert. What I think is a dessert, I don't know. So we've shown that there's this infinite staircase of infinite sets. For every infinite set, you can find a bigger infinite set. So there's no largest set. There's no largest cardinality, because if you found that largest cardinality, you could just take the power set of something that is that big, and then that would be bigger. Okay, so that's already, there's no. Not only is there more than one kind of infinity, there's infinitely many infinities. Okay, so now we can ask another question. So this is Hilbert's first problem, and it's called the continuum hypothesis. And this is a very celebrated problem. Hilbert in 1900 was a very, very famous mathematician, among mathematicians, I guess, as famous as a mathematician usually gets. And in 1900, he said, okay guys, we gotta sit down and we gotta figure out some stuff, because there's some holes in our knowledge that need to be filled. And he was very influential at the time, and sort of dabbled in a bunch of different disciplines, and was very good at a bunch of different mathematical disciplines. And for that reason, he was able to sort of see things from above in a way that not everybody can. And he set out with these problems, 23 problems, of things that he thought needed to get done in the 20th century. And the first one, the one that he chose to put first on his list, was a continuum hypothesis. What is the question here with the continuum hypothesis? The question here is whether or not I can find some kind of set, which I'll just call S. It doesn't really matter, S for set, that is between the sizes of the real numbers and the natural numbers. Okay, so because of the way we've defined things, the natural numbers. Or because of the way we define the natural numbers, I guess, the natural numbers are the smallest kind of infinity. There's no smaller infinity than the natural numbers. But the real numbers, we know they're bigger. The question is there something that's bigger than the natural numbers but smaller than the real numbers? And David Hilbert, it turns out, was a little bit optimistic when he asked this question, because when he asked this question, he assumed that there would be an answer. In 1963, a guy by the name of Paul Cohen, I guess like the date and his name aren't that important, but what he proved that you can't prove either way. Okay, so let's just we're not gonna work through his proof. In case you were hoping for that. So what does that mean? He proved that you can't prove either way. It means that if you assume that that there is such a set, then you get something totally consistent, and you can totally do math like that, and there's no problem. But also, if you assume that there's no such set, then that's totally consistent, and it works, and you can do math like that, and you don't run into any problems. So we have no way of knowing whether or not, in the real world, as it were, whether such a set exists. We can put it in our axioms. We can make an axiom that yes, this is true, and we can make an axiom that no, this is false. And either way, mathematics will work just fine, or as fine as it was working before. And if mathematics makes sense, then it makes sense either way here. So that was sort of the dessert in the sense that this is a kind of a mind-blowing result that you can't prove. You can't prove either the positive or the negative of this question. So I hope you enjoyed this fantastic meal of math. Are there any other questions? All right. Yes.
So, does math work differently depending on whether it's true or not?
It works differently in a sense. So you'd be able to talk about the power set of this guy because this guy exists, but you wouldn't be able to talk about the power set of it if it doesn't exist, right? But it turns out you don't come out with any contradiction. So you don't have a way of knowing you don't have a way of placing the size of the power set of this compared to the size of the power set of other things in a way that would lead to a contradiction, right? You have this new thing, you have this object which is some set that you've claimed is between these two sizes, and you just have it. It's just sitting there. Okay. All right. Cool.
What's your favorite number?
What kind of number?